Good day everyone, we are Group 7. I am Ayan Jan Mundo.
I am Jessel Bintisan.
I am Ariel Pagador.
And I am Rachel Mutia.
I am Ines Moratalia, and we are here to discuss traffic assignment.
By definition, traffic assignment models are used to estimate the traffic flows on a network. These models take as input a matrix of flows that indicate the volume of traffic between origin and destination, or O-to-D pairs. Traffic assignment is a key element in the urban travel demand forecasting process. The traffic assignment model predicts the network flows that are associated with future planning scenarios and generates estimates of the link travel times and related attributes that are the basis of benefits, estimations, and air quality impacts. Here are the aims of traffic assignment procedures. First, to estimate the volume of traffic of the links on the network and possibly the turning movements at intersection. To furnish estimates of travel costs between trip origins and destinations for use and trip distribution. To obtain aggregate network measures. To estimate zone-to-zone travel costs for a given level of demand. To obtain reasonable link flows and to identify heavily congested links. To estimate the routes used between each origin and destination. To analyze each O-to-D pairs that uses a particular link or path. And lastly is to obtain turning movements for the design of future junctions. And lastly is to obtain turning movements for the design of future junctions. So this is the link cost function. As the flow increases towards the capacity of the stream, the average. So this is the link cost function. As the flow increases towards the capacity of the stream, the average stream speed reduces from the free flow speed to the speed corresponding to the maximum flow. This can be seen in the graph shown below. So this is the graph. That means traffic conditions worsen and congestion starts developing. The interzonal flows are assigned to the minimum paths computed on the basis of free flow link impedances. That means traffic conditions worsen and congestion starts developing. The interzonal flows are assigned to the minimum paths computed on the basis of free flow link impedances. But if the link flows were at the levels indicated by the assignment, the link speeds would be lower and the link travel time would be higher than those corresponding free flow conditions. So the minimum path computed prior to the trip assignment will not be minimum after the trips are assigned. A number of alternative procedures are done to converge this difference. The relation between the link flow and link impedance is called the link cost function and is given by the equation as shown below, where t and x is the travel time and flow, respectively on the link, where the t and the x is the travel time and flow, respectively on the link, and TO is the free flow travel time, and K is the practical capacity, and A and B are the model parameters for which the value of A is equal to 0.50 and B is 4.0 are typically used. So we have different types of traffic assignments. Traffic assignment is a crucial step in transportation planning and modeling, where the task is to allocate the travel demand, which are the trips generated by people or goods, to the transportation networks available routes and modes. And there are several types of traffic assignment methods, each with its own characteristics and use cases.
So first type of traffic assignment is all or nothing, or A to N. So in this method, each trip is assigned to a single road, the most attractive. So this is usually the shortcut way. So it assumes that travelers are rational and always choose the best route. So typically used as an initial assignment for other algorithms. So for example of all or nothing assignment is to demonstrate how this assignment works. An example network is considered. This network has two nodes having two paths as links. Let us suppose a case where travel time is not a function of flow as shown in other words. It is constant as shown in the figure below. So in the figure of the two-link problem with constant travel time, we can see that t sub 1 is equal to 10 and t sub 2 is equal to 15. So, and the total flows from 1 to 2 is given by U sub 1 to 2 is equal to 12. Since the shortest path is link 1, all flows are assigned to it, making x sub 1 is equal to 12 and x sub 2 is equal to 0. Next is the equilibrium assignment. Equilibrium assignment assumes that travelers seek to minimize their own travel cost, which includes both travel time and congestion-related delay. Now, models the dynamic interaction between travelers and the transportation network, seeking a traffic flow pattern that reaches equilibrium. So, common models include user equilibrium or UE and system optimum SO assignment. Another example of user equilibrium assignment is the user equilibrium assignment is based on Wardrop's first principle, which states that no driver can unilaterally reduce his or her travel cost by shifting to another road. So, user equilibrium conditions can be written for a given zero dash link, whereas f sub k quantity of c sub k minus u equals to 0. Then c sub k minus u is greater than or equal to 0. So where f sub k is the flow on path k and c sub k is the travel cost on path k and u is the minimum cost. So equation level can have two states. So if c sub k minus u is equal to 0 from equation 10.1, then f of k greater than or equal to 0. So this means that all used paths will have same travel time. Next is if c sub k minus u is greater than or equal to 0, then from equation 10.1, f sub k is equal to 0. This means that all assumed paths will be travel time greater than the minimum cost path, where f sub k is the flow on path k, c sub k is the travel cost and on path k, and u is the minimum cost. So, assumptions in user equilibrium assignment. So there are three basic assumptions. So number one is the user has perfect knowledge of the path cost. Second is travel time on a given link is a function of the flow on that link only. So number three is travel time functions are positive and increasing. The solution to the above equilibrium conditions given by the solution of an equivalent nonlinear mathematical optimization program. So where is the assumptions in user equilibrium? This is equation 10.3. So where k in the equation is the path, x sub a is the equilibrium flows in link A, and t sub a is the travel time in link A, and f sub k rs flow on path k connecting to 0 dash link where r dash s. So q sub r is separate between r and sun. Then this is a definitional constraint and this is given by this equation 10.4. So the equations above or the equation in the previous slides are simply flow conservation equations and non-negativity constraints respectively. These constraints naturally call the point that minimize the objective function. This equation states user equilibrium principle. The path connecting 0 the pair can be divided into two categories. Those carrying the flow and those not carrying the flow, in which the travel time is greater than or equal to the minimum 0 day. If the flow pattern satisfies this equation, no motorist can better off by unilaterally changing routes. So all other routes have either equal or heavy travel times. The user equilibrium criteria is thus met for every 0 dash D pair. The UA problem is convex because the link travel time of functions are monotonically increasing function, and the link travel time, a particular link, is independent of the flow and other links of the networks. So to solve To solve such convex problem, Frank-Wolf algorithm is useful. So for example, let us suppose a case where travel time is not a function of flow as shown. In other words, it is constant as shown in the figure below. So as we can see, the figure 10.3, this is the tooling problem with constant traveling time function. So T sub 1 is equal to 10 plus 3 R sub 1. Then T sub 2 is equal to 15 plus 2 R sub 2. So minimum of Z sub times R is equal to integral of 0 x sub 1 10 plus 3 x sub 1 times D x sub 1 plus the integral of 0 to 1 to 15 plus 2 15 plus 2 times R sub 2 times D times R sub 2. So this equation is subject to this one. So x sub 1 is x sub 1 plus x sub 2 is equal to 12. So substituting x sub 2 is equal to 12 and x sub 1 in the above function will yield the unconstrained formulation as below. Next type of traffic assignment is the SO or System Optimum Assignment. So the System Optimum Assignment is based on Wardrop's second principle, which states that drivers cooperate with one another in order to minimize total system travel time. This assignment can be thought of as a model in which congestion is minimized when drivers are told which roads to use. So obviously this is not a behaviorally realistic model, but it can be useful to transport planners and engineers trying to manage the traffic to minimize travel costs and therefore achieve an optimum social equilibrium. So equation 10.5 is minimize Z is equal to summation A x sub A times T sub A times x sub A. So in this equation, where x sub A is the equilibrium flows in link A and T sub A is the travel time in link A, and if sub K is the flow on path K connecting to 0 dash D pair RS, and the Q sub RS is the trip rate between R and S. So for example of System Optimum Assignment is this one. So to demonstrate how the assignment works, an example network is considered. This network has two nodes having two paths as links. So let us suppose a case where travel time is not a function of flow, or in other words, it is constant as shown in the figure below. So this tooling problem is with a constant travel time function. So this is the equation 10.10, 10.11, and this is the equation 10.12. From the equation, to differentiate the above equation to 0 and solving for x sub 1 and then x sub 2 leads to the solution x sub 1 is equal to 5.3, x sub 2 is equal to 6.7, which gives z sub x is equal to 327.55.
So next topic is other assignment methods. So this topic, we have the proportional assignment. It is also known as the fractional assignment or gravity model. It allocates a portion of each trip to multiple routes based on some attribute. Example, travel time, cost, distance, and attractiveness of each route. Then often used in conjunction with AON assignment to define results. Next assignment is the stochastic assignment. It introduces randomness or uncertainty into the assignment process to account for variations in travel behavior. Then it is also useful for modeling real-world situations where travelers may make choices with some level of randomness or uncertainty. assignment is the DTA, or the Dynamic Traffic Assignment, where it focuses on the assignment of trips in real time or overtime periods. Then accounts for congestion dynamics and the changing conditions of the transportation network, and it is often used for traffic management and control, such as adaptive traffic signal systems.
Next, we have multimodal assignment. When we say multimodal, it's a transportation term. It deals with the assignment of trips using multiple modes of transportation, such as car, bus, train, bicycle, and walking. Allows planners to evaluate the effectiveness of integrated transportation systems. Type of day assignment takes into account variations in travel demand and network conditions throughout the day. Useful for analyzing congestion patterns and planning infrastructure improvements. It's a process of estimating how many people will use different modes of transportation in a given area and time period. Travel demand is not constant throughout the year. It can vary significantly due to seasonal factors such as holidays, school schedules, tourism, and special events. Next, we have the capacity restraint assignment. Considers the capacity limitation of various network elements, example, roads, intersections, when assigning trips. Ensures that trip assignment do not exceed the capacity of the network. Is the hierarchical assignment. Splits traffic assignment into multiple levels, considering different levels of decision making. Example is the strategic, tactical, and operational. It is also useful for large-scale transportation planning. Hierarchical assignment in traffic assignment models allows for a more detailed and accurate analysis of transportation systems by considering factors such as different transportation modes, network levels, user classes, and temporal variations. It enables a nuanced understanding of traffic flow, optimizing transportation planning and management. Disaggregate assignment. It focuses on individual trip assignments, providing a detailed view of how specific travelers choose routes. Disaggregate assignment in traffic assignment involves analyzing transportation systems at a fine-grained level, considering individual trips and travel behavior. This approach provides more detailed insights into traffic patterns, allowing for a better understanding of the interactions between travelers and the transportation network. Disaggregate assignment is useful for modeling diverse factors such as mode choice, route selection, and travel time variability, leading to improved accuracy in transportation planning and decision making.
The last stage of traffic demand modeling is the traffic assignment. So there are different types of traffic assignment models, and these are the all or nothing, user equilibrium, and system optimum assignment models are the commonly used models. So these traffic assignment methods are essential tools for transportation planners and engineers to model and analyze traffic flow, congestion, and performance of transportation networks under different scenarios. The choice of method depends on the specific goals of the analysis and the available data and resources. In conclusion, traffic assignment is a fundamental process in transportation planning and modeling that plays a pivotal role in understanding and optimizing the flow of traffic within transportation networks. It involves allocating travel demand to specific routes and modes, helping planners and engineers make informed decisions about infrastructure's improvements, congestion management, and transportation systems optimization. Through a series of steps, including trip generation, trip distribution, mode choice, which is optional, traffic assignment, traffic flow simulation, also optional, evaluation and scenario testing, traffic assignment provides a valuable insights into how travelers use the transportation network under various conditions. This information is essential for addressing traffic congestion, improving travel efficiency, enhancing mobility, and making data-driven decisions in urban and regional planning. Traffic assignment is not a one-time process, but often iterative one, requiring accurate data collection, model calibration, and the consideration of various scenarios. With the continuous growth of urban areas and the increasing complexity of transportation systems, traffic assignment remains a vital tool for creating more efficient, sustainable, and accessible transportation networks that benefit both individuals and the communities. And I think that would be all. Thank you.